I'm Dan Graboy, and this is Life in Time of Pandemic, and I'm here with Ellen Zweibel. Hi, Ellen.
Hi, Dan.
Ellen, you are a professor of astronomy and physics at UW-Madison. So does that mean that your field is actually astrophysics?
It means that my field is plasma astrophysics. People who work in theoretical astrophysics, which is what I do, usually have some specialty in physics that they're particularly interested in. And for me, it's plasma physics. And there's a great plasma program at the UW, and that's why a lot of it is in physics, and that's why I have a joint appointment with physics.
Okay, so there's a lot for us to deal with here. First of all, what is plasma?
Plasma. So the ordinary gases, like the atmosphere that we breathe, um, every molecule has an equal number of positive and negative charges. It has a nucleus, which is positively charged, or more nuclei in the case of a molecule, and then electrons that kind of form a quantum mechanical cloud around it. And in a plasma, the electrons are stripped off those positive nuclei, and so you have free positive charges and free negative charges. And that means that the gas is much more responsive to electric and magnetic fields.
Okay, so in 11th grade chemistry, we were taught that there are these orbitals. They're basic, that it's the nucleus is like the sun and the electrons are like planets orbiting. Is that theory kind of gone kaput at the kind of plasma level you're talking about?
Well, I think it's a useful picture. It's a useful way to think of an atom. Two important differences are that, as far as we know, the Earth could be, there's an energy associated with every orbit. And the farther away, in the case of a planet, from its parent star is, the closer that energy is to zero, but it can be any number. In the case of an atom, you can only have special numbers, and those are called the quantum mechanical energy levels. And you can calculate, it's difficult, but you can calculate what those energy levels are, and they're what we say quantized, because they can only take certain values. So that's one way in which the little solar system picture is not complete. The other way is that, and this is hard to swallow, that we shouldn't really think of the electron as being in a definite place and moving with a definite speed at every time, the way we can think of a planet. We should think of the electron as being more kind of like a cloud, where you can say, well, it's probably sort of over here. And there's a trade-off, which is that in order to know exactly how fast it's moving, we have to give up essentially all information about where it is. And conversely, to know where it is, we have to forget about how fast it's moving. Now, you're a musician, okay? I know. So there's kind of an analogy with a tuning fork. So with a tuning fork, if you want to make an A sound, you let the tuning fork ring for a long time. And the longer you let the tuning fork ring, the more pure that sound is. But if you strike the tuning fork and then choke it off immediately, the frequency, you get this whole kind of burst. You get this burst of sound that's at many frequencies. And there's a similar trade-off between position and speed with a quantum mechanical particle. Does that make any sense?
It does. Now, am I right that Einstein was troubled by all of this uncertainty?
Einstein was very troubled. Yeah, Einstein was very troubled by quantum mechanics.
Understandably, every time I've had it explained to me, it goes into my head and pops out very quickly and seems slippery. The whole concept of what's happening in our world at the tiny, tiny high energy level is really slippery. Is it for you, or are you able to capture it in numbers and probabilities and feel comfortable with it?
So I've kind of trained myself to avoid risk. So just, if you're walking on a trail over a mountain pass and, there's sheer drop-offs on either side of you, you can stick to the middle of the path and be fairly relaxed, or you can kind of skirt the edge and live dangerously. And I have to say, with quantum mechanics, I kind of stick to the middle of the path. I use quantum mechanics. I deal with very large numbers of particles, so I don't have to know exactly what every particle is doing, and so on.
Okay, so what does all of this have to do? We're talking about tiny particles, but you're in the astronomy department. And when I think of astronomy, I think of somebody with a telescope looking out into the universe. You're telling me about electrons and where they may or may not be. So what am I missing?
So the way we learned about the universe is from light, and not just optical light, but the whole electromagnetic spectrum: radio waves, infrared, ultraviolet, X-rays, gamma rays. It's because matter radiates that we know anything about it. And so our key to how plasmas, and pretty much every astronomical system in the universe is a plasma, is we can only access it through light. Now, recently, there's a very exciting development, what we call multi-messenger astronomy, which is seeing the universe through gravitational waves and high energy particles, either high energy charged particles or high energy neutrinos, which have no charge. And so the birth of so-called multi-messenger astronomy is giving us, just volumes, just undiscovered realms of phenomena that we could only speculate about before.
So there's all of this stuff going on, and yet from day to day, and I'd add, especially during this pandemic that we're probably at the beginning of, life seems to unfold the same all the time. There's a regularity to it. I'm not aware of any neutrinos or any disturbances in the force or any quantum uncertainty in my life. I know whether my dog is alive or dead. I know my toast doesn't toast in the toaster unless I push the button down. And yet people like you are always telling us that the universe is a mass of uncertainties. How can I reconcile I won't say boredom, but the regularity of my life under house arrest during the pandemic with what you're telling me?
Okay, so what I said about electrons, finding it difficult to localize where they are, this is part of what we call the wave-particle duality in quantum mechanics. And so light, electrons, they have wave-like aspects, so sort of fuzzy packet-like aspects, and particle aspects. Now, according to the theory of quantum mechanics, we do too. And yet, I don't think you and I look fuzzy to each other. So how can this be?
Well, we're talking over Zoom, so sometimes we do, but I don't think that's what the theory is talking about.
But forgetting about that. So, and the answer is that that the wavelength or the size of the packet, the wave packet that corresponds to an everyday object like this beautiful mug, which comes from the Very Large Array National Radio Astronomy Observatory in New Mexico, is very, very tiny. I mean, theoretically, this mug is a wave, but the actual mug is much bigger than the wave. So we can treat it, we can say exactly where it is. I know better than to drop it, and so on. And I can see where you are, you can see where I am. So a lot of quantum mechanical uncertainty only shows up at really microscopic, beyond the microscopic is where it shows up. So now the predictability, so again, the laws of dynamics allow us to predict where big, so we can say where the Earth will be in its orbit, and we can predict what, where the stars will be. I think maybe my most riveting moment as a kid when I was, thinking about what I would be when I grew up was reading about an occultation of a star by the planet Jupiter. And so this was in Jupiter passed in front of a star, and it was very useful astronomically because when that star passed behind Jupiter and was before it faded to invisibility, they could see what the atmosphere of Jupiter was made of through the chemical fingerprint that it left on the light from that star. So that's when we learned that the atmosphere of Jupiter is mostly methane and ammonia, had not been known up until that time. And, I found that very intriguing that every substance has a distinct fingerprint in light. But what I found even more amazing was that scientists could predict that one tiny dot was going to pass in front of another tiny dot. That, this could actually be done, and done very precisely, so that, you could be ready with your telescope. And so the universe, the macroscopic universe that we live in, does follow laws that, have been tested. I mean, we can, we don't just have to guess that Jupiter's going to pass in front of this star. We can actually verify that this happened. So, and it's because the quantum mechanical world really only intrudes on very, very tiny scales or very, very high energies.
So I want to get back in a minute to macroscopic versus microscopic, but first I have a follow-up question about your mug.
Okay.
If your mug is made up of particles or waves or whatever it's made up of, how come it doesn't have holes in it? How is it possible that it holds your coffee?
Well, it's full of holes. I mean, you were probably told the same thing in elementary school that we were, that matter is mostly empty space, and you should be able to walk through walls and everything like that. And this is true. And so this mug is actually quite transparent to certain forms of light. If you had X-ray vision like Superman, you could see that this mug is not very clean inside. It's full of coffee grounds, but you cannot see that. So certain forms of radiation can penetrate matter all the time, and we can target very precisely, for example, in radiotherapy of tumors. We can, not only can we create particles and light that are so energetic that they can pass through body tissue, but we can calibrate their energy such that they stop in just the right place and irradiate your tumor. So as light or beams of particles pass through, an object like a coffee cup or the human body, they do interact with the molecules that are there, and they exchange some energy and they get knocked off course a little bit. But we can predict, based on lab experiment and theory, we can predict, very accurately how much that happens. And we could make X-rays, for example, which could see the grounds in the coffee cup, but not pass below and see the floor and see that the floor has not been washed in some time.
Well, you didn't need to admit that, but we appreciate it. So I understand that certain wavelengths of light can pass through the coffee cup, but coffee can't pass through the coffee cup. So let me press you on that. Why can't the coffee pass through when the light can pass through?
Because the coffee, so for couple reasons. The coffee cup keeps its shape, right? It's not just some collection of molecules that were kind of heaped up in a certain shape. They're interact, it forms a solid with some regularity. I don't think it's a crystal, but there are forces between the particles in this coffee cup, and anything that, in order to kind of skirt between them, you have to successfully penetrate those forces. Now my coffee is fairly acidic because I like it strong, but if it were super acidic, it would pass through the coffee cup. It would erode, the nice enamel and so on. So yeah, the kinds of structures that solids form. I mean, that's actually a fascinating topic that I'm not an expert on by any means.
You are an expert on this microscopic versus macroscopic view, and I'm wondering if you as a scientist are bothered by the fact that the motions of the planets and the stars seem to be absolutely predictable, and the motions of tiny things seem to be absolutely unpredictable. Does that drive you crazy?
So, so I'll tell you, actually, there's an aspect of it which drives me crazy, which is that, so yes and no as to how predictable the motions of the planets are. So there's a macroscopic phenomenon called dynamical chaos, so if the motion of the solar system were chaotic, there would be apparently unpredictable events. For example, moons of some of the planets might kind of go flying off in a way that could not have been predicted. And what that would mean would be that, their orbits were actually not very regular, and, two moons had passed close to one another and exchanged some energy, and one of them went flying off. And it was actually, so people have thought, actually going back a long time, is the solar system stable? Are the orbits of the planets now, the way they were pretty much a billion years ago, and will they be that way in the future? And this issue was finally settled. I think it's been settled by a very long computer simulation of the solar system that went back and put in as many bodies as they knew about. And voila, it stayed pretty regular. Now, new comets are appearing all the time. Comets that have maybe gravitationally scattered off some other body, and they never made it to the inner solar system before, but here they are. And and they're messengers from the deep past. There are comets that have been orbiting at great distances, for hundreds of millions of years or billions of years. So there is this phenomenon called dynamical chaos that arises in many body systems. And sometimes that's described in terms of the so-called butterfly effect. And, you've heard, the butterfly beats its wings and everything turns out differently. And what this means, and what it means in physics, is that you can try to reproduce all the exact features of an experiment, but it may be sensitive. There may be certain sensitivities to getting it exactly right. It may be impossible to get it exactly right. Okay, so there's chaos. Now, in quantum mechanics, we don't really have a perfect description of chaos. And a place where this comes in is, so I mentioned a while back that atoms, like the hydrogen atom, has quantized energy levels.
So just to remind people, that means that the energy levels are fixed.
That's right.
And there are no in-between energy levels.
That's right.
Electrons.
But there are an infinite number of energy levels. And as you go to higher and higher energies, they become closer and closer together. And what distinguishes the way you make a plasma from an ordinary gas with neutral atoms is that you impart just enough energy to the electrons that they can go free. So every atom has a binding energy, or every electronic state has a binding energy, where if you give it, the electron, that much energy, it'll just decouple from the nucleus. And you can calculate what those energies are. And we don't understand the dividing line very well between whether an electron is bound or unbound. Okay, and that kind of relates. So as you pass from unbound to bound, you encounter some of the same issues that you discover in dynamical chaos.
Okay,
And
so you just talked about comets orbiting,
mhm.
and that raises this question I've always wondered about, which is why is everything orbiting? Everything we see is orbits, and there's circles or ellipses. Why
Mhm.
isn't stuff just flying around?
Well, some stuff is flying around. It's very hard to quantify, but we know that if you kind of travel throughout our galaxy, you you will encounter a star every few light years. It's the average spacing between stars, and we know, thanks to pretty interesting set of observations, that many stars have planets. And we look for planets around stars. The way we see planets is by their effects on stars. Now, whether there are free planets just kind of zooming around, um, we don't really know. They would be very hard. They would be very hard to see. And we do know that a lot of the matter in the universe is dark matter, and that dark matter may take the form of sort of loose objects, certain loose objects flying around. So they're not particularly tied to any star, any galaxy, even any galaxy cluster.
So it has been in the news, although not recently, since there's only one subject of the news right now, but it has been in the news in the past that there are many planets being discovered. And we used to not know, I think, if there were a lot of planets, and now it's clear that there are. How do you find a planet? And
How
have
do you
you ever found one?
No, I have not personally found a planet. So, so the way the first planets were discovered was by very, very slight motions of their parent stars. So just as, so we think of the Earth going around the sun, but actually the Earth and the sun are in a mutual orbit. And so the sun is in some sense going around or it would, let's just say there was only one planet in the solar system, the sun and the Earth. The center of that system would be slightly displaced from the center of the sun. The Earth is not orbiting the exact center of the sun. It's orbiting a point that's very close to the center. And the sun is making a very, very tiny orbit around. Now, the most important body in the solar system that changes the motion of the sun is Jupiter, because it's further away from the Earth, but it's much, much more massive. And so this very, very slight wobble in the position of a star is what allowed us to detect the first planets. And this actually led to a tremendous surprise, because Jupiter is what we call a gas giant. It's mostly gas. It's got this huge envelope of gas, and it's at a very cold temperature. And so you would think if you moved Jupiter, very close to the sun, that it would heat up and the gas would just kind of evaporate. So our expectation was that, if you looked at a typical system of planets around a star, that the rocky planets like the Earth would be the inner planets, and the gas giants would be the outer planets, the way they are in the solar system. But this method of detecting planets works best for very massive planets, because they're the ones that exert an appreciable tug on their parent star, and the closer they are to that star, the greater the pull. So the first planet that was discovered, I believe around the star 51 Pegasus, was actually much closer to its parent star than Mercury is to the sun. So Mercury is the closest planet, so it's very close to its parent star. It's what we call a hot Jupiter. And the hot Jupiters, depending on what kind of star they're orbiting, the hot Jupiters are, sort of heating up and losing some gas. And so then that leads to the question, how do you even form a hot Jupiter? Can you only form a Jupiter under cold conditions? And that led to a whole theory of how planets can migrate in radius. So your question about the regularity of the solar system, the existence of these hot Jupiter planets tells us that that the orbits of planets can actually change a lot. Now, what can change the orbit of a planet is another planet or another star or some mass of, so you may know a little bit about these flybys. Like, so right now there's this mission called Parker Solar Probe, which was launched from the Earth, and the objective is to visit the sun. Okay. Now, you cannot just blast off a rocket from the Earth pointed at the sun and expect it to go there. Okay.
Why not?
Because you're blasting it off from the Earth. What keeps the Earth at the distance from the sun that it is a property called its angular momentum, which relates to its spin. And it's very hard to get rid of angular momentum. Okay, it kind of represents, it represents kind of the orbital motion. And in order, you cannot destroy angular momentum. You have to change it somehow, you have to give it to something else. You have to exert some kind of force on it. So if you blast off a rocket from the surface of the Earth, you would say in the wrong direction. So going in the reverse direction from the way the Earth is going, you've kind of given it a push in the right direction of getting rid of its angular momentum, but there's not enough power on Earth to take away so much angular momentum from that poor little rocket that it'll go straight toward the sun.
So is this like jumping out of a moving car? You can't just go sideways. You'll keep going forward while you're in the air, sort of like that?
That's exactly what it's like. You think, you want to get rid of the person, you don't like the person you're with, I'll just jump out of the car. Well, no. So what we've done instead, for decades with these probes is work out this intricate system of gravitational assists. So what Parker Solar Probe does is it flies into the outer solar system. It has a gravitational interaction with another planet, sheds some of its angular momentum, and then when it comes back to the sun, it can get a little closer. And it does that again and again. And that's the way all these things do. And so somehow these hot Jupiters were able to do the same thing. They were able to find some reservoir to deposit their angular momentum in, and that enabled them to get very close to their parent star.
So just about every sci-fi movie or TV show features people in a spaceship using the slingshot effect to correct some previously insoluble problem. And it sounds like this is related to that, and there may actually even be some truth behind the sci-fi.
So yeah, so obviously I can't speak to exactly what they do at any particular, but yeah, this basic slingshot idea, it's using somebody else's gravity, taking advantage of somebody else's gravity to get rid of your angular momentum.
So you know so much stuff, and I'm just grateful to have all these basic things explained. When you are doing your research, which is for all of us who are professors here, research is a big part of our job. What are you doing? Are you sitting at a computer doing math, or are you just sitting in a chair thinking about how things might work? Or what's your actual flow?
Okay, well, here's a little bit of my actual flow.
Okay, hold that up again for a second so people can see a little higher. Okay, good. So there's a lot, I see some Greek letters, and I think I see a tangent and maybe an alpha. Mm-hmm. And it's clearly an equation because there's an equal sign and a max and a minimum of something. So what is all that seems like gibberish to us?
So what is all that? So a lot of my work is done with PhD students, and I've been doing I've been trying to calculate I'm trying to do a plasma physics calculation that describes how very high energy particles called cosmic rays, this is a large part of what they study, how they interact with electromagnetic waves.
So tell us what a cosmic wave,
cosmic
did you say?
ray is a charged particle, usually a proton, and it's traveling at very close to the speed of light. And how it got that way is a whole other subject, which we could talk about later if you like. But they're there. They were detected. They've actually been known about for hundreds of years, but the reason we call them cosmic rays, which is a kind of vague term, is we didn't really know what they were until almost 100 years ago. So anyway, so this calculation is very complicated. It has a lot of steps. Some of it is on the computer. Setting it up is writing down equations on pieces of paper. And so a student who's working with me on his PhD project is doing it also. And what we decided was that we would each do it independently. He would do it, I would do it, we would see if we got the same thing, because there were just so many opportunities to make mistakes in this thing. And when you're doing research, it's, how do you check yourself? It's it's new. Nobody knew it before. That's why it's research. So we decided to do it independently, see if we get the same answer. Well, we don't. Okay. Now, I don't know if he's right, if I'm right, or if we're both wrong. But what we agreed was that we would each write up very careful notes and then share notes with each other and check each other's notes. So I was doing that this morning, and I came to a place in his notes which were very clear. And I thought, I don't know if I agree with that. So what you see here is my attempt to, sort of the thought process that I went through that make me now suspect that there's an error in his notes. So I wrote all this up in a word processing language called LaTeX, which allows you to write equations. And I sent it to him, and I said, well, here is a place where you and I differ. Please take a look. Let me know what you think. So as far as, he hasn't written back last time I checked, we'll talk about it the next day or two. So that's kind of typical. That's kind of typical of my process. A little bit of, so a certain amount of thinking. So I go running every day, and sometimes I don't really think, try to think things through on my run, because I would just fall over my own feet. But somehow, I don't know, something happens, wheels are spinning kind of somewhere. And sometimes I come back with an idea or a realization or something like that. And then there's a certain amount of writing on paper, most of which goes in the recycling bin. And then there's some really great mathematical software that you can kind of use to do experiments. So sometimes seeing, if you're actually evaluating a formula, you might have to evaluate it many, many times, and it would take a long time, so you can do it on the computer, that sort of thing. So that's a part of what I do. And then comparing it, does this make sense? Do I understand these trends? You don't accept answers at face value. You try to see if they're consistent with other things you know.
Does it bother you that there's probably an extremely small number of people in the world that understand what you're doing? Or do you feel like you're not doing this for the mass public, you're doing it for the advancement of understanding of the universe?
Yeah, so that's a good question. And that actually gets to, one of the issues that's come up during this pandemic, which is that there is a community. There is a community of people who are very conversant in this stuff. And although I don't expect them to read my calculations in detail, sometimes they do. And we have a common language. We can talk about it. And, and I know that there aren't that many of those people, although there are probably more than you think. But usually we see each other a few times a year at conferences, And in fact, this whole project that I just described grew out of a multi-week stay I had at a workshop which brought together a lot of people who work on these things. A lot of ideas and research projects kind of came out of that. So, so there is a community, and I try to write, when I write a paper that's published in a scientific journal, or when I give a talk somewhere, I try to make it intelligible, not only to the core of that community, but to people who know something about it, something on the periphery, and then, sort of trying to communicate with them and make them, see if they think it's important or if it applies to anything that they're doing. So communication is actually a big part of what I do. I also think that that there is a place in society for curiosity-driven research. And sometimes people say, well, NASA was all worth it because we invented Tang or something. And it's okay. We have Tang. Tang came out of the space program, but I think that people have always, they have always kind of asked what is the world made of? How did we get here? What will happen? Why is the universe the way it is? And of course, I only do the smallest part of it. And I don't do the most profound questions, but I do try to kind of chip away at a little bit of that.
You have very generously spoken 3 times on my Soundwave series, in which you're telling about a particular topic over which you have a lot of expertise, but talking to people like me who don't know any science. And of course, I'm appreciative, but I'm always amazed that your talks are comprehensible. And do you think it's important to try to take your knowledge, which is up here, and speak to us down here about it? Does that matter in some way to you?
Well, they're not that different. They're not that different. My dad, I work in the language of mathematics, and not everyone follows me there. My dad was a machinist, and loved science, was very interested in science. He was a machinist, and I think he had a reputation in his factory, for being smart. And he told me one day, and this is really a story about the American workplace. It'll just take a couple minutes. Some guy who was on the night shift, this was a factory that made nuts, machines like nut after nut after nut. And this guy's job, and he was on the night shift, was to, make sure this machine had metal and that the nuts went in the barrel. And he asked my dad, he said, John, if I put a little dent in that barrel, would it hold fewer nuts? Would I fill it up more quickly? And you can sort of see what he was thinking. And my dad said, well, sure, imagine that you turn the barrel over and drove over it. It wouldn't hold any nuts. So, and I remember thinking, I learned how to think from this guy, because that's how I think of things. I take a problem and make the most extreme version of the problem that I can. Don't just put a little dent in the barrel, actually drive over it. It won't hold any nuts. So taking the extreme in a problem. So there are all these ways of thinking that people have about everyday problems, or any kind of problem. And these ways of thinking about things carry over to very abstract things too. And when I feel, so, you can look at this formula and, you're probably thinking, how does she know that's right? I mean, you were too polite to say so, but, how does she think this is right? Well, the answer is, when I start working on a problem, writing down the equations for that problem, it's very easy to make mistakes because I don't know what they're supposed to look like. But after I've been working on the problem for a while, it's almost like climbing on a jungle gym or something. I mean, you just, when you reach for the bar, that bar is there. Okay, you don't reach in the wrong place. And when you work on a problem for a while, oh, excuse me, that's a phone. When you work on a problem for a while, you sort of inhabit it. Hold on a second.
Ellen is fielding a phone call, and she will be right back. And we have some more questions, and we need to talk more about the pandemic and how that affects her research as well. So stay tuned. We will continue in just a minute. I'll mention that this interview is happening on May 9th of 2020. So we have been, the university has been shut down since April 13th. So we're entering, since March 13th, so we're entering almost at the 2-month mark of our shutdown. So yes, continue, please.
Well, I think I said everything I was going to say about this. Our instincts when we do research, it becomes, if you're willing to work on things for a long time, it really kind of merges with everyday experience. And and I realized that if I tried to, if I just showed somebody an equation on a bus and said, see the top and the bottom, they're about the right size, I think I was nuts. But you really do develop a feeling for it. And so then kind of finding, it's the structure is there. The structure is there. And you can talk about these esoteric things with a common language with people. You can.
I want to get back to macroscopic versus microscopic. And what I'm wondering, since you have told me that things are fairly regular on the macroscopic level and very unpredictable on the microscopic level. My question is, are there people trying to make one thing out of those two things?
Oh boy. So we can describe what's going on in the solar system quite accurately with Newton's laws of gravity. To be more exact.
Sorry, but they were formulated around when? When are we talking?
Oh boy, let's see. 17th century. I'm terrible with dates.
Okay, but a long, long time ago. We've had these for over 400 years.
A long time ago.
Okay.
It's been with us. And, so Newton's laws, for example, were used to predict that the planet Neptune had to exist. We didn't know that, we thought that the solar system, the last planet was Uranus. It turns out to be Pluto, actually. Well, Pluto's now a dwarf planet. But the small discrepancies in the motions of the planets from Newton's theory led to the discovery of Neptune. So it works very well in the solar system. And it seems to work, most people would agree that it works very well, kind of on an ordinary scale.
It works for the coffee staying in your mug and not slipping through the cracks.
Well, gravity, it's not gravity that's doing it, actually. It's other kinds of forces, more electrical forces. But then Einstein came up with his own theory of gravity. And Einstein's theory of gravity is necessary for more refined predictions. For global positioning satellites, for example, they have to use Einstein's theory to get it perfectly right. And
what would happen if they used Newton's theory instead? I'm driving from here to my cabin in the woods, and I'm using an Einsteinian GPS system. What happens?
Well, you want to use an Einsteinian GPS system.
Newtonian. I'm using a Newtonian.
If you use a Newtonian GPS system, so if your cabin is not too far away, you might just get to the same resort, but you get to somebody else's cabin, okay, which they might defend aggressively. And if you're going to a cabin in another state, you probably won't get to the right town. And
what if my cabin's in the Adirondacks in north of New York?
North of New York.
So it's 900 miles away. Not
I
gonna,
think you'll get to, I think you'll be in New York.
I'll be in the state of New York.
So the problem is that time, one of the predictions of Einstein's theory of gravity is that time depends on where you are in a gravitational field. Now,
I don't understand that, so you better explain it to everybody.
okay, so what it means for GPS is that, so the way GPS works is we think we know the speed of light, and it's actually the same. That's one of the tenets of Einstein's theory. Light is always traveling at the speed of light. And we know exactly how, so if we know exactly how long it takes to go from one place to another, we know how far apart they are. That's a cornerstone of GPS. But in order to know how long it takes, our clocks have to be running at the same rate. So if my clock goes for 12 ticks and your clock goes for 13 ticks, we know that it took 1 tick. Okay. But now if I'm sitting many miles above the surface of the Earth, the gravitational field that I'm experiencing is a little bit different. It's a little bit weaker than the gravitational field that you're experiencing. And so my clock will run at a different rate, and I will count ticks. You and I will not agree on the number of ticks.
And I don't think probably you can explain this here, but why should we just accept that our clocks are running at a different rate?
Well, one way to think about it, and I think this is mostly correct, is that light. So there is. So you're familiar with the Doppler shift, which
Yes,
is
when
that.
the train goes by and goes, or a
Yeah,
car.
yeah. So in Einstein's theory of gravity, in Newton's theory of gravity, gravity travels across flat space. In Einstein's theory, gravitating masses actually curve space a little bit. And the gravitational force that you feel is different from a force, say, exerted by an electrical charge or something like that. It really corresponds to the curvature of space. And so light is traveling on a curved path, and it needs a little bit of energy to crawl out of. So an extreme example of this would be that, so if something is falling into a black hole, okay, so imagine that, like a little clock is falling into a black hole. The clock is really going faster and faster as it's falling into the black hole. You would see the clock move, the hands on the clock moving more and more slowly, assuming that you could still see it. The clock would actually you would never quite see the clock go into the black hole. I know it's terrible.
It's
it would.
terrible. It's
You would never see
mind-bending.
it. You would never see it. That last image of the clock would slowly fade, but it wouldn't disappear when you threw. So a much less extreme version of this goes on with the Earth. And so
So we're at GPSs now. So the satellites are up in the atmosphere or above the atmosphere, and
yeah, they're above. They're in a slightly different gravitational field than the gravitational field of the Earth. The Earth is also rotating, which gives you another effect, but that's much smaller. So so that's an example where Einstein's theory, even though the difference in arrival time is incredibly tiny, that's an example where you really have to use Einstein's theory if you want to get to your cabin. Now, what about?
Just to interrupt for 1 second, people who say that who cares about Einstein? We need to feed ourselves and keep clean and get rid of pandemics and be healthy. Well, actually, here's a practical application of Einstein's theories, which affect every single person who navigates by GPS, which in olden times, 4 months ago, was basically everybody.
So I actually don't have GPS.
Well, you have a phone probably.
Well, I have this very primitive little flip phone.
No, that's wonderful. I like that a lot.
I don't know. I don't like to see too many executive functions to devices. Um, okay, so to get back to your original question, do we ever have to use quantum mechanics with gravitation? That's what you asked, the microscopic and the macroscopic. And the answer, as far as we know, is that very early in the history of the universe, we did. Because if the universe was born from something like the Big Bang, it was really very tiny and very hot. And it was described by the laws of quantum mechanics, but also the laws of gravity. And so one of the great frontiers in physics is putting those two things together. And
So there are people working on exactly that topic, is putting them together, and you have to go back in time in order to see where they split apart. Is that right?
Yeah, so sometimes this is called a unified field theory. The idea that, so the forces of nature that we know about, there's electromagnetism, and then there are the strong and weak nuclear forces. So you might ask yourself, well, if the nucleus of an atom is composed of protons, which have a positive charge, and neutrons, which have no charge, the protons should repel each other. How can you keep a nucleus together? And the answer is that there are these so-called nuclear forces. There are the strong and weak nuclear forces that keep atomic nuclei and subatomic particles together. And if you go back far enough in time to when the universe was very, very hot, you couldn't have atomic nuclei. Everything kind of ran together. And according to, I guess it's the expectation that gravity will one day be described in the same way as those other forces. And that's called the unified field theory. And Einstein spent his later years, most of his career actually, trying to develop a unified theory. He realized that there would have to be one, but he was unable, he did not succeed in this.
It's pretty daunting to think Einstein couldn't do this, but maybe I could do it. I mean, but there must be people working on it.
Well, people are working on it, and science is, it is sort of incremental. People stand on the shoulders of giants, and there have been many giants that work on this problem. It's a few minutes to 11, and I should really go.
Yes, I wanted to ask you one final question, which was, it sounds like the pandemic has very little effect on your research. You're able to sit at your computer, collaborate with your doctoral students, do your equations without too much difficulty. You don't need to get to a telescope and look at stars for what you do. Obviously, teaching, we all know teaching over Zoom is complicated and challenging, but are you not slowed down at all by the shut-in that we're experiencing?
No, I feel that I am slowed down. I mean, I feel what you said is exactly right. I have it much easier than scientists, say, who have to get to a lab. And I feel incredibly fortunate that I still have a job where, because many people don't. I mean, we're going to be furloughed, but at a level so far that's livable. But yeah, it's hard to say. I've had many discussions with people about what exactly makes this so difficult. And it is difficult for all of us. And, partly we're all distracted. Am I going to get sick? Does my throat feel scratchy this morning? Why is it scratchy? Am I hot? There's some level of worry for everyone. And my mother's 90, so spend a certain amount of time worrying about her. There's that. There's also that I don't think we communicate as well. Students would pop by my office when we were all in our offices. Students would pop by my office. Now I'll get an email message, can we talk on Skype later? Can we talk on Zoom later? A lot of the spontaneity has sort of leached out of it. Face-to-face discussions, writing on the blackboard, so here, my student wrote notes for me. I read the notes. I wrote him an email. he'll read my email, he'll get back to me. The whole thing will take longer. And, you know, just as you cannot ride a bicycle up a steep hill slower than a certain amount, or you tip over, you cannot slow research down below a certain amount. Otherwise, you just kind of forget what you were doing. So, yeah, so I think I've already partially adapted. I think other people have, but obviously I don't know what the future holds.
And none of us does.
None of us does.
But I want to thank you for talking with me and unraveling some of these mysteries. I'm sure everybody has many questions and we'd love to spend hours, but the day has only so many of those. So thank you.
Opportunity.
Well,
So the reason I have to go is I have to do a curbside pickup, which many of us do.
That's a fact of modern life.
Yes.
Thank you so much.
Take care.